Hi, this is Anna Johnson, Lab 4, Magnetic Braking with Faraday. The purpose of this lab is to study the varying magnetic field created by a bar magnet falling through a tube of aluminum foil. We will observe the magnet falling through the conductive tube and note observations, model the magnet and its interactions, and compare the computational predictions with observed data. This lab focused on Faraday's law, which relates a time-varying magnetic field to an electric field whose path integral around a closed path provides an EMF. This EMF can produce a current which can create a magnetic field and exert a force on the initial source. In this experiment, the magnet was the source of the time-varying magnetic field and the tube acted as a conductor for the induced current. Some fundamental concepts used were Faraday's law, magnetic flux through a ring, Newton's second and third laws, and magnetic field of a bar magnet. And a quick summary of the results, the time for the magnet to fall computationally was 2.78 seconds, and experimentally it was 1.9 seconds. For the experiment, we used a bar magnet, a roll of aluminum foil, and a ruler to measure the dimensions of the foil tube. The dimensions can be seen, length being 30.46 centimeters, our diameter being 4.55 centimeters, and inner diameter of 2.56 centimeters. We also used a timer to measure the time it took for the magnet to travel down the tube. I did 5 trials and took the average for a more accurate result. For each time measurement, I positioned the bar vertically before dropping the magnet down the tube. To get a more accurate reading for time, I recorded the process in slow motion so I could see more exactly when the magnet entered and exited the tube. Next, we created a computational model to simulate this experiment. The bar magnet is modeled as a point dipole, and the aluminum tube was modeled as a stack of independent conductive rings. After setting up the initial conditions, we calculated the magnetic field due to a bar magnet at a relative position to the magnet. The function dipole B at the bottom was used in the previous lab. We then calculated the rate of change of magnetic flux through each ring by the falling magnet. This function is seen in the first picture of code, or this picture of code called calculate d flux d analytic. The equation for this function can be found in a previous lecture video and is 3 times mu naught times mu mag times distance times speed times the radius of the ring all squared, or radius of the ring squared, all over the denominator 2 times the radius of the ring squared plus distance squared to the power of 5/2. Faraday's law was then used to find the current by the falling magnet in each ring, and the Biot-Savart law was used to calculate the force exerted on each ring by the falling magnet. Using Newton's third law, we calculated the force exerted on the magnet by the tube of current-carrying rings, assuming that the tube was in a fixed position. The net force of the magnet was calculated by summing the force already found with the force of gravity. Lastly, Newton's second law was used to update the position of the falling magnet and display it. The graph on the right shows the velocity of the bar magnet as a function of time, or graph on the left, sorry. It appears that the magnet reaches a terminal velocity while in the tube, and the model on the right predicts the magnet being in the tube for around 3 seconds. Accounting for a large error in experiments conducted by humans, such as not pressing the timer accurately or angling the tube on accident, this model is probably more accurate than my experimental results. And some conclusion questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Keeping Ohm's law in line, which is V equals I times R, this shows that resistance and current are inversely proportional to each other. So a decrease in resistance would cause current to increase, and therefore an increase in current would increase the time it takes for the magnet to fall through the tube. And finally, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The flux of the magnetic field through the tube would decrease along with the magnetic force on the bar magnet. This would result in less resistance, so that the magnet would fall faster through the tube, so the time it takes for the magnet to fall would decrease overall. Thank you for listening.